Example 2 on the cylindrical shell method. Use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis region under the curve y equals x squared from 0 to 1. Anytime it says from something to something, that's from x equals unless otherwise stated. So we're starting at x equals 0, ending at x equals 1. I just figured a quarter scale on that would be pretty good. And y equals x squared is going to start at 0, end at 1 squared, which is 1, so I did a quarter scale on y-axis also. I kind of always make a decision before I start graphing what the scale is going to be to kind of get an idea of enough space to create room to be able to do stuff. Because again, otherwise if it's just a one-to-one scale, everything's going to be right here in this little box. Kind of hard to draw and be able to get any detail in there. So if I just get y equals x squared, just squaring all the numbers from 0 to 1 going by 0.25s. 0 squared is 0, 0.25 squared is 0.0625, which is a quarter of the way to 0.25. And 0.25 squared is 0.5, which would be here. Oh wait, so 0.5 squared is 0.25, there we go. Should be right there. 0.75 squared is 0.5625, which would be about here. And then 1, 1 would be right there. So that would just be some points along the way. It's just a parabola. And again, it says from 0 to 1, y equals x squared would actually go off the other direction also. So here and there and so on. But we want to start at x equals 0 and x equals 1. So we're only looking at this piece. And we're also considering all the way to the x-axis, so underneath the curve to the x-axis. So our official region here is just right in here, like so. Again, we always want to shade our original region. That helps establish where we're going for the radius and height of this cylinder that we're going to create. Okay, the rotation this time is about the x-axis, so our rotation goes this way, which means that if I just reflect that, did the wrong flip, up, down, there we go. Just drag that right there. We're looking at that shape right there, and we're going to be, there's our shape that we're trying to find the volume of. Now, just one disclaimer here. The disk method is much easier on this one than the cylindrical shell method. So going back to the last chapter, if we were to draw a circle, so if I were to just draw like a cross section right here, find the area of that cross section, so here's my cross section, the radius is y, right? And y equals x squared, and we're going left and right, so we want it to be a dx integral, so x squared. Area of that would be pi times x squared. So the volume would be the integral of pi times x to the 4th dx. We're starting at x equals 0, ending at x equals 1. Right? And that would work, and that would get me pi x to the 5th over 5 from 0 to 1. Pi x to the 5th, so pi times 1 to the 5th, so pi over 5 minus 0, so they're units cubed. When the washer method or disk method works, it's much easier. Okay? What we're going to get for the cylindrical shell method here is going to be pretty ugly. You're not going to like it very much, but it does give us some technique and some ideas on how to use the cylindrical shell method better on a not very difficult problem. Again, just like any other math that we did, we would do some difficult concepts from the easier problem to practice the skills to be able to handle harder problems when the other method doesn't work. Sometimes this method doesn't work. The cylindrical shell method is necessary, so we want to practice it and get good at it. But just know that pi over 5 units is the right answer. So, with the technique they're asking us to do, the cylindrical shell method, if we get to that, a little too racy in there, there we go. So if I were to draw a cylindrical shell again, let me reiterate, this is a hollow shell. So let me just put it wherever, it doesn't matter where. But imagine that we have a shell of almost no width that's hollow. So it's like a paper towel tube, hole in the middle. And then we're stacking these one little bit bigger, 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 bigger radius until we create this whole solid. And the height, let me clean that about the right spot there. There we go. So there's one of our shells right there that is going to be creating this. And again, we're doing infinity of these shells, starting with a radius of 0 and working our way to a radius of 1. And again, that's what we're expanding on if you imagine that these radii are growing, growing, growing. So the radii are growing vertically, so we want it to be a dy integral. All right. The two things I have to establish are the height and the radius. So the radius is right here, and the height is right there. So that's y, which is the radius. And that is the height, but it doesn't equal x. All right, so just realize that height's not always going to equal x, radius isn't always going to equal y, and vice versa. Okay, height is horizontal in this case, so it's going to be about x, but x is right here. That's x. And you can see there that x is not the height, but x is related to the height because if I take the height and I take x and add them together, I make all the way to the edge of this thing, right? That's always 1. From the y-axis to the back end of this shape, no matter where I'm at, it stays 1 all the way through, right? That never changes. The bottom of this region, of this solid, and the y-axis are always 1 apart. So what I can see from this picture is forever and for always that x plus h has to equal 1. And again, h is the thing I'm looking for in terms of x. H has to do with x, but h doesn't equal x. H actually equals 1 minus x. All right? Again, the radius equals y. So each time you do these problems, height's going to be about x or y, radius is going to be about x or y, but they aren't going to necessarily equal x or y. They might equal something about them. So h doesn't equal x equals 1 minus x. Height actually equals, or the radius actually equals y. All right? That's fine. That can happen. Okay, if we rotated it somewhere else, maybe the radius is also something like 2 plus pi. I don't know, something like that. So again, you have to establish things that are true. It's always segment addition postulate that's happening. This is always going to be the height. This is always going to be x. They're changing. This is always going to be 1 that never changes. There's a relationship between the three things to create that expression. Now, as I said, when you're doing the cylindrical shell method, what we're adjusting is the radius. So the radius is changing each time we do this. So we want to start at y equals 0, end at y equals 1. We need everything to be about y. So the radius is good to go, but the heights in terms of x, we need to fix that. And x is related to y in that sense, that y is equal to x squared. Because again, that's where the height and x are being dealt with, is by this curve. That curve is created by that equation. That's the relationship between x and y there. So I know that x squared equals y. That means x is equal to plus or minus the square root of y. And officially it is plus or minus the square root of y. So then we have to look at our region to establish which one we want to pick. The regions in the first quadrant, the x values start at positive 0 and they end up at positive 1. So everything's positive, right? We want x to equal the positive square root of y because we're taking the positive values of x there. So even though x could equal plus or minus the square root of y, we're going to throw out the negative because we're only dealing with positives in this problem. That changes h into, instead of 1 minus x, it's going to be 1 minus the square root of y. And since integration is involved, I'm going to go y to the half power. So now heights in terms of y. Okay, those two things are very important in every one of these problems. When you use cylindrical shells, find the height and the radius in terms of the variable you care about. Okay, if I'm doing a axis of rotation on a horizontal axis, I want everything about y. If I'm doing on a vertical axis of rotation, I want everything about x. So R is about y, H is about y, everything's ready to go there. The only other thing I need is the interval, and it's a y interval. So the circles start, or the cylinders start at y equals 0, and they end at y equals 1. Again, the interval is all about the radius. The radius is here, the radius is vertical, so vertically it starts at 0, ends at 1. There's our interval. Once you have all that information, the formula always is the same. Volume is equal to 2 pi from A to B of RHD, in this case y. That changes. Okay, again, you made a decision for what it is for this problem. It's a y problem, so dy is what we're going to get for this one. It's always 2 pi. R and H are going to be whatever these are, A and B or whatever those are. That's how you construct the volume formula. So 2 pi, 0 to 1 of R, which is y, times H, which is 1 minus y to the half, dy.
Question.
Yes?
Where'd the 2 pi come
It's just part of the formula. So going back to the initial thing, it's just the fact that it's a number, I pull it out of the front. I mean, officially it's inside the integral, but I can throw it outside the integral. I just don't like to get in the way.
from?
So, but it's just part of the formula. Going back to just basic geometry, if we have a cylinder with a radius of r and a height of h, the perimeter of the base is 2 pi r, the height of the cylinder is h, and the lateral surface area, which is what we're trying to look at here, is just 2 pi rh. That's where the formula comes from. That's the lateral surface area. So again, what we're considering here are a bunch of hollow cylinders. We're finding the surface area, the lateral surface area of each of these hollow cylinders, and we just keep adding them up. We're going through infinity of them with the integral. But again, the 2 pi came from the fact that the perimeter of the base is 2 pi r. That's where it comes from, but again, it's just it within the formula there. That's the right place, good. All right, so if I go on to integrate this, I'm going to get y minus y to the 3/2 dy. Same integration techniques as before. We want to make the simplest integral possible. This is a product of things. This is just a simple polynomial structure. Antiderivative of y is y to the 2nd over 2. The antiderivative of y to the 3/2 is y to the 5/2 over 5/2, which is times 2/5. Once I integrate it, the dy disappears, the integral symbol disappears. Now we just have to substitute 1 and 0 in. If I substitute in 1, more white paper to write on here. All right. If I put in 1, I've got the 2 pi out here. I'm just going to get 1/2 minus 2/5. If I substitute in 0, I'm going to get 0 minus 0. Of course, 0 is gone. All right, common denominator of 1/2 and 2/5 is 10. So if I get a common denominator of 10, that's going to be 5/10 minus 4/10, which makes 2 pi times 1/10, which makes pi over 5. When it comes time to take a test on this, know that I'm not going to specify a technique, but when you try and do that disk method and the inside and the outside go to the same curve, this is the only way to go. All right. Otherwise, if you can just make a nice cross-sectional area that just goes from the axis to the curve itself, the disk method much quicker. And just to remind you, there was the cross-section radius of y, which is x squared. The area of that was pi x to the 4th. The integral was volume is equal to pi x to the 4th dx from 0 to 1. And they got us pi over 5 units cubed. very little mess, right? Much easier. But that's not always available to you. This is sometimes necessary to be done. And again, being able to handle that in an easier problem like this, as opposed to a more challenging problem that might come up maybe tomorrow, it's helpful to practice the skill, get good at it, and understand where things are coming from, understand how to construct the integral properly. That's the main key to this, that we figure out all these pieces to create the integral, to create the answer. Integrating is whatever it is, you get the expression you get, you integrate it. That's not that bad. We practice that enough, but creating the proper integral is going to be the key to getting the problems right on these. So that's what you have to practice to get good at.